but have you ever actually wondered how slow it really is? Let's find out. On the left, we've got a simple C program adding numbers from 0 to 100 million, and on the right, the exact same logic written in Python. Both start at the same time. And look at that. The C program finishes in just 0.08 seconds, while Python takes around 6 seconds. That's more than 10 times slower, doing the exact same task. So, what's really going on here? What actually happens when you run a .py file that makes it so different? Today, we're opening up Python's black box to see what's happening under the hood, from how your source code turns into bytecode, to how the interpreter executes it, and even why things like the global interpreter lock even exist. By the end of this video, you won't just know that Python is slow. You'll understand why it is, and how tools like PyPy and Cython try to make it faster. When you run a Python script, it doesn't go straight to execution. Python first compiles your code into bytecode, a compact set of instructions for the Python virtual machine. You don't usually see this step, but it happens every time. For example, if we define a simple function for adding two numbers and run dis.dis, Python shows a human-readable disassembly of its bytecode. Instructions such as load fast, binary op, and return value. These aren't machine instructions like C or C++ generate. They're Python's own virtual instructions, which the interpreter executes one by one. So, even though Python feels like a purely interpreted language, under the hood, it always compiles your code first, then runs the resulting bytecode inside the Python virtual machine. The Python virtual machine is simply the interpreter loop that lives inside CPython source code, specifically in a file called cval.c. It's a massive C loop that runs forever, fetching, decoding, and executing each bytecode instruction one at a time, like a chef reading a recipe step by step. That extra layer of interpretation is one reason Python is slower than languages like C, which compile straight to machine code and run directly on the CPU. But Python's object model also adds overhead. Everything in Python, integers, strings, lists, even functions, is a PyObject that stores not just its value, but its type, reference count, and behavior pointers. This gives Python its flexibility and dynamic typing, but it also means that even 10 plus 10 requires multiple pointer dereferences, type checks, and object handling. Python does apply small optimizations, like interning integers from -5 to 256, to avoid recreating them. But beyond that, new objects are constantly created and destroyed. To manage this, CPython uses reference counting for immediate cleanup and a cyclic garbage collector for more complex cases. Safe and automatic, but not without performance cost. Now comes the part every developer has heard about, the Global Interpreter Lock, or GIL. The GIL ensures that only one thread can execute Python bytecode at a time. Sounds restrictive, right? It is, but it's also intentional. CPython's memory management isn't thread safe, and the GIL prevents multiple threads from modifying objects at the same time. So even if you start two threads doing heavy computation, you won't see a big speedup, because under the hood, the GIL is constantly handing control back and forth between them. It's not a bug, it's a deliberate design choice that keeps single-threaded code simple and C extensions fast. So when people say Python is slow, what they're really describing is a combination of trade-offs: dynamic typing that checks everything at runtime, interpreter overhead that processes one bytecode at a time, object boxing that turns even tiny numbers into complex structures, garbage collection that occasionally pauses to free memory, and the GIL that keeps threading safe but serialized. Meanwhile, C skips all of this. It compiles straight to machine code, operates on raw memory, and lets the CPU run at full throttle. In other words, Python takes the scenic route, slower but safer and far more flexible. And that's exactly why Python remains brilliant. You can write 10 lines of Python to do what might take 100 lines of C, and when you call libraries like NumPy, TensorFlow, or PyTorch, you're actually calling highly optimized C or C++ under the hood. Python gives you readability, flexibility, and still lets you borrow speed when you need it most. And the story doesn't end there. The Python ecosystem is evolving fast, with projects like PyPy, which adds JIT compilation to turn bytecode into native machine code on the fly, Cython, which lets you write Python that compiles to C, Numba, which jits numeric functions for speed, and even new interpreters like Rust Python and Mojo, exploring modern, parallel safe designs. CPython itself is improving too. Version 3.13 introduces sub-interpreters, a major step toward eventually removing the GIL altogether. So next time you hear someone say Python is slow, remember, it's not because it's lazy. It's because Python chooses clarity, safety, and flexibility over raw speed. Every part of its design, from compilation to garbage collection, is a trait that makes developers more productive, even if it costs a few milliseconds. And honestly, that's a trade most of us are more than happy to make. And that wraps up all sections. If you found this helpful, make sure to subscribe to the channel and stay tuned for more Python and system design interview prep content.